7.8.3, finding roots with polynomial division. This will be an application lesson of everything else that we learned previously in this chapter. To find the zeros of a quadratic function, we've got three methods. We can factor it, we can use the quadratic formula, or use the graph. Though sometimes a graph of a higher degree polynomial, it'll show us the zeros in the form of x-intercepts. But that's only in the case the x-intercepts are real numbers. And to find exact zeros of many of these higher degree polynomial functions, we'll have to go back and use long division. Here's an example. What are the zeros of the function p of x, which is a fifth degree polynomial function, of x to the fifth minus 6x to the fourth plus 20x cubed minus 6x squared plus 99x minus 54? Well, start looking for the zeros. I'm going to look at the graph I have. That's a graph of the function, and it looks like here, here, and here. So at x is 1, x is 2, and x is 3, I believe I have 3 zeros already. Now, if I wanted to go back and check to see if x equals 1, x equals 2, and x equals 3 are in fact zeros, everywhere I have an x, I could plug in a 1. And I'd type that into my calculator. And if it equals 0, which in this case it does, I know that it is most definitely a root. Same thing works if I was checking for when x is equal to 2. Plug it all into my calculator. And once again, it would equal 0. And the same thing works for x equals 3 in this case. So from this, I was able to find 3 factors of this fifth degree polynomial. And those 3 factors are x minus 3, x minus 2, and x minus 1. And I find those just from looking at where my x-intercepts are. Now I need to take a step back and look. I have 3 x-intercepts. That's good. And those are only 3 roots of this polynomial. So I will go back and look at what my graph is doing. If I see any bounces, I'll know, well, there's a double root there. I go back and look at each place where my x crosses the x-intercept, and I do not see any. So I have no double roots. Then I believe there may be a triple root, which I'd look for something that looks like that there. On no such occasion does this occur when I look at my x-intercepts. So I only know that there are 3 real roots, and I have no double roots, and I have no triple roots. This must mean my last 2 roots are going to be complex. In order to find these complex roots, I still need to find another mysterious factor of my polynomial. So, I'm going to need to use long division. Before I can use long division, I must distribute the 3 factors I know together. So, let's begin. Let's FOIL x minus 3 multiplied by x minus 2. So x times x is x squared. X times negative 2, negative 2x. Negative 3 times x, negative 3x. Negative 3 times negative 2, positive 6, all still multiplied by my x minus 1. Combine like terms to find x squared minus 5x plus 6 multiplied by x minus 1. Now I need to distribute my x squared minus 5x plus 6 throughout my x minus 1. So x squared times x is x cubed. X squared times negative 1 is negative x squared. Negative 5x times x is negative 5x squared. Negative 5x times negative 1 is plus 5x. 6 times x is plus 6x. And 6 times negative 1 is minus 6. Combine like terms to find this to equal x cubed minus 6x squared plus 11x minus 6. Now by combining those three factors, I have a new factor of my original fifth degree polynomial. Now I need to divide that original fifth degree polynomial by this new factor I found. So x to the fifth minus 6x to the fourth plus 20x cubed minus 60x squared plus 99x minus 54 is all divided by x cubed minus 6x squared plus 11x minus 6. This, just going back to using long division. So how many times does my x cubed term go into my x fifth term? Answer simple, x squared times. Now time for that division step. X squared multiplied by x cubed, x to the fifth. X squared multiplied by negative 6x squared is negative 6x to the fourth. X squared multiplied by 11x plus 11x cubed. X squared multiplied by negative 6 minus 6x squared. Subtract x to the fifth minus x to the fifth is 0. Negative 6x to the fourth minus and negative 6x to the fourth is 0. 20x cubed minus 11x cubed. Well, that's just 9x cubed. Negative 60x squared minus negative 6x squared. That's going to be negative 54 x squared. Bring down my plus 99 x to bring down my minus 54. Now I need to make my x cubed look like 9x cubed. Well, all I have to do then is multiply x cubed by 9. So 9 times x cubed, 9x cubed. 9 times negative 6x squared, well, that's negative 54x squared. 9 times 11x plus 99x. And 9 times negative 6, negative 54. Do the subtraction. I'd find this 0, which is very good because we know we are dividing by a factor, and there should be no remainder when we're dividing by a factor. So I now have this new number here, x squared plus 9, which is the only factor I am missing from my fifth degree polynomial. Now let's use it to find the two remaining roots. X squared plus 9, that is definitely a quadratic polynomial. So I can use the quadratic formula. X squared plus 9, well, that's the same as 1 times x squared plus 0 times x plus 9. So when going back and using my quadratic formula, that's going to be the opposite of 0 plus or minus the square root of 0 squared minus 4 times 1 times 9 all over 2 times 1. This is equal to plus or minus the square root of negative 36 over 2. And that equals plus or minus the square root of 36 times the square root of negative 1 all over 2. Well, I know the square root of 36 is 6, and the square root of negative 1 is I. So I can write this further as plus or minus 6i over 2. And that even simplifies to equal plus or minus 3i. Now I just found my two final roots. If I'm looking to write out all of my roots, I can write the following. Originally, we had found that I have a root at x is equal to 1, 2, and 3. And from our previous page, we found that we have roots at both 3i and negative 3i. Now, if the question asks me only to name the roots or the zeros, I would be done here. But if the question asks me for factored form, I'd have one additional step. Since this problem prompted me, giving me general form, I can use it to write factored form. In general form, if I'm looking for the leading coefficient of my highest exponent, which in this case is 1, I know that will tell me what my a is equal to in factored form. So since my leading coefficient is 1, a is equal to 1. So as I'm writing factored form, y is equal to my a, which is 1, multiplied by x minus the first 0, which is 1, multiplied by x minus the second 0, which is 2, multiplied by x minus the third 0, which is 3, multiplied by x minus the fourth, which is 3i, multiplied by x minus the fifth 0, which is negative 3i, so that's the same as x plus 3i. And that is the factored form of this polynomial. Now let us recap the steps we went through to finding the roots. So I initially simply looked at the graph and found all of my x-intercepts, which were x is equal to 1, 2, and 3. Then I noted that's not all of my roots. I still needed an extra piece, so I knew I had to use long division. My next step distributed x minus 3 times x minus 2 times x minus 1 to find this new root to that fifth degree polynomial. I could then use the root I found to find that last remaining root that I did what it was, which in this case was x squared plus 9. Now, x squared plus 9 doesn't exactly tell me roots. But what it does tell me is that this factor will break down into two roots. One of these roots is going to be x plus 3i, and the other one will be x minus 3i. And that's because in this step, we use the quadratic formula to find those two roots. Then, by what this equation was asking us, all we had to do was write down our zeros. But, in insight to future lessons, we also simply took our zeros and wrote them in factored form.